Hey, recording's rolling. It is Tuesday, January 6th. I have a lab lineup you guys say. It's going to be a lab day. And last class is to pretty much exactly the class period, so we're done perfectly. Right, but right before I get to that, I gave you guys the lab page. So I'll show you guys what's going on with that. But before I get to that, yesterday I asked for some volunteers for, well, over at Ralph Williams Elementary School, there's a link to a map exactly where it goes opposed to Google Classroom. So it's just across I-95. Right. But on Thursday, January 15, from 5 to 7 p.m., there's going to be a STEAM night. And I did get some of you guys to volunteer for that. So if you did volunteer yesterday, I sent an email around and got all that right. Now, there is actually a second event I didn't go over yesterday. It's Tuesday, January 13th. These are, of course, elementary school students. They're having a science fair, and Santa is asking for science fair judges. Now, this would actually be during the school day. So if you wanted to do this, you'd have to miss your class during the day. So that's extra stuff. So if you are interested in that, go ahead and email Mr. Engler over at the elementary school. If you volunteered yesterday, then you already have his email address because what is email that around. So that's extra appearance in that. Right, so, oh yeah. Yes, Ralph Williams Elementary School. Yeah. Okay, so then, you guys do puzzles. Alright, so here, my honors class had these puzzles, and then AP, I gave you guys chapter 10, 11 by your book. So by AP's book, this actually covers 2 units. They used to have it one unit. They broke it into 2 small units. Right, so chapter 10 corresponds to unit 5, and chapter 11 corresponds to unit 6. Reminder, I did open the AP classrooms for that, so if I have to bump the due date back, then I'll do that too, but that's all. So if you want to go start reading the questions, something like that. All right, so yesterday I went through a bunch of posters with you guys, mostly focused on actually Unit 5, and I didn't quite get to what's considered part of Unit 6, but I think I'm going to take a break from that and come back to those later. All right, and give you guys the opportunity to do this lab today. All right, so this lab is all about torque. All right, remind you guys what torque is. You guys remember torque is this turning moment. It's R cross F. You guys, this cross here, this cross product, really means that you take this vector R and this vector F, and you only multiply what components? The parallel or the perpendicular? Perpendicular, exactly, right? Only the 90-degree components actually do anything, right? Like if I push this way on the wrench, it never turns the wrench. Okay? But only. So if you push at some angle, you need to take the sine of that angle, the angle between the Okay, so you guys know that. Okay, and the lab I'm having you guys do today is going to be in 2 halves. So there's going to be a seesaw half like this. Okay, seesaw half. Okay. And then there's going to be a scaffold half. And I'll show you guys both of these, what I'm looking for. Right. Now, both of these, the guiding principle is that the torque goes to 0. Now, the forces also go to 0. Isn't that your 2 conditions now for equilibrium? Actually, I have both of them right here. The forces go to 0, and the torque goes to 0. Okay. Right. So let's start with the seesaw. Okay. Now, make sure you're on the right side. All right, so you guys see the side, there's a single spring scale holding up each meter stick. You guys see that? Okay. I'm not on the side, I'm going to flip this over. I'm not on the side yet where there's a couple of spring scales holding up each meter stick, so we'll save that for later. Okay. So everybody's on the single spring scale side? Everybody see that? Okay. So, of course, write your name here. What I'm going to have you guys do is put the spring scale right at the 50 centimeter mark of the meter stick, which is at its own center of mass. Okay, so that'll simplify this a little bit. Okay, guys, okay, and then hang a couple of lab weights. Maybe you have like this lab weight and this lab weight. Okay. Now the question is there's gonna be a universal question for all 4 parts of this lab, all 4 parts. Okay, which is you're gonna solve for some mystery weight. Right, you guys see that? Okay. So your end goal is, can you calculate one of the lab weights? Now, obviously, you're going to know what they are. Because, for example, 200 grams. Let's review. 200 grams weighs approximately how many newtons? 2. Yeah, it's like 2 newtons. Right? And it's like 1.96, but usually we just call it 2 newtons, right? So if you do this whole process and you go through torque, which I have you guys out here in the and suppose you do this whole thing and you get like 1.91 newtons. Would that be pretty close to 2 newtons?
Yeah.
Yeah. And you say, oh, I must have done everything correctly. Right, so let's get that. Right, so hang the spring scale right at the center, right, and hang 2 lab masses. Right. Now, one of these No, obviously you're going to know what both of them are. This might be 1 Newton and 2 Newtons, but let's make believe that you don't know what one of them is. You guys got that? Make believe you don't know one, so you can calculate by the end. Okay. Okay. So this says x left, that could be the left position. Okay, and the center mass of the meter stick and also the spring scale is going to be at the 50 centimeter mark. Okay. So label however many newtons this guy is right here. How many newtons? Right, if it's like 2 newtons, you can put 2 newtons. If it's 5 newtons, put 5 newtons. Okay. And then see here where it says x left minus x scale. Okay, see that? And I gave you a negative value. Because guys, if this was at 30 centimeters and this is at 50 centimeters, what's 30 minus 40?
20.
That'd be negative 20. And I gave you the negative to ensure you get that. Right. Okay, and then you can calculate the torque. Oh, because you'll have a lever arm and a force. Now, look at this setup right here. You guys see this says pivot point scale? You guys see pivot point scale right here? Right. So, part of the well, an interesting thing about torque is that technically you can sum the torque about any particular point. Like you don't necessarily have to pick this pivot point, even though it might be the most intuitive. So I'll start with this point because it is intuitive, but I'll show you guys later that you don't necessarily have to pick that point. So relative to this point, if this point's like the door hinge, think of it that way. Guys, if this is the door hinge, okay, you guys see that I have this left lever arm here? I'll call this like R left. Okay, and this downward force right here, call this F left, which is a weight, right? Guys, what is weight measured in? Grams or newtons? Weight is in newtons, right? Mass is in kilograms, weight was in newtons, weight's the force in newtons, right? Do you guys see that if this is the door hinge, I have this R crossed with this F. In fact, if I was using right hand rule, I would call it a positive torque, wouldn't I? Okay. But if you probably just call it counterclockwise. You guys see a counterclockwise torque right there? Tau for torque left, right? And then there's this mystery weight over here, which is also offset some distance. I'll call this R right. Okay, and maybe it has a different weight. I'll call it F right. You guys wait for the force. Okay. You guys see that's creating a clockwise torque? Call it torque right, clockwise torque. You guys see that? Right. And if I was using right hand rule, then I'd start from this pivot point and say, here's your R, here's your F, and then see how my thumb is pointing into the page. Right. And that would be called a negative torque. Right. But you just like clockwise. Right. Now guys, what do you think the sum of these two torques is? 0. Has to be 0. If it's all in equilibrium, it's just hanging out there at rest. That'd be equilibrium, wouldn't it? So here, let's go back to this table. So it takes this force multiplied by this distance, and I get this counterclockwise torque. You guys see that? Guys, everybody look here. See what's going on? Okay. Then over here, guys, if you have a spring scale right at the defined pivot point, well, it's kind of like if I push right on the door hinges of the door. Is that ever going to open the door? If I push right on the hinges of the door, can I ever get out of here?
No.
So that's why it's going to come out to 0 torque because there's 0 distance from that point. So the spring scale can read anything. In fact, you know what it has to read. It has to read the sum of all the weights, the weight of the meter stick and the 2 weights that hang, right? But it doesn't matter what the spring scale is because times 0, so it gives you 0 torque relative to that point. You guys get that? Right? Then there's this mystery weight. And what's wait, hold on. What did I just oh sorry. That's the meter stick itself. Okay. That's guys, it's the same explanation. Guys, doesn't the meter stick have some weight? Even though the meter stick weight is distributed over the entire meter stick, as long as it's uniformly distributed, is it okay to treat the weight as a point mass of the center mass? Yeah, actually that's what the center one is, right? This one on the right is the spring scale holding up, but it's still going to be 0 for the same reason, because it's at the same pivot point. You guys see that? Right, so it's 0, 0, 0, right? But you guys said the sum of the torque has to be what again? 0. So let's say you do all this right here. Let's say you get like negative 5 Newton meters. I'm just making something up. Guys, if this comes out to negative 5 Newton meters, which would be the sum of the torque, because negative 5 plus 0 is negative 5, then what does this last torque have to be? Well, the sum of the torque has to be 0. So if this is negative 5, the last torque has to be positive 5. You guys see how you're going to go from here to here? Yeah. This box is just the negative of this box. Do you guys see that? If this is negative 5, this has to be positive 5. Okay? Okay. Now, you do know where the mystery weight is located. So can you guys find this lever arm? Right, and that's right here. It tells you exactly how to find it. It says take that position minus the pivot location at the 50 mark. Okay? Right. So guys, if you have this torque and you know the location of the mystery weight, how do you get this force? Okay, torque divided by R equals force. You guys see that? Okay, that's exactly what this is. Point right here. Okay, you guys get that? Okay. Again, if you had hung on this lab weight, it says 200 grams, so that's approximately 2 newtons. You want this number to be really close to 2 newtons. If you get like 1.91 newtons, okay, oh, that's really, really close. I must have done everything correctly. Right? If you get something like 57 newtons, like, okay, something's definitely messed up. But if you get like 1.91 or 2.05, then that's like right in there. Okay? Right, guys good? Are you guys ready to move on to the next part?
Yes.
So it's kind of like part 1 of 4. Right? Now over here, moving to the left side of the page, this is the exact same setup. Because going from the right side to the left side, you do not have to change anything about your setup. Same spring scale, same weight, right? Maybe same mystery, weight, right? What changes is your perspective, and that's right here. You see it says pivot point defined as the 0 centimeter mark. Right. All right, guys, pay close attention here. This is a point I was trying to make at the end of class yesterday. This gets more abstract. You guys ready to get more abstract? What we're going to do is we're going to change the pivot point from the center where the spring scale is, which is most intuitive anyway. We're going to slide it over to the far end of the meter stick, which is labeled 0 centimeters. You guys got that? Now, guess what happens to the sum of the torque relative to that point? It's still 0. Right? But the individual torques are different. And here's what they are. Now, this left weight actually causes what kind of torque? Clockwise or counterclockwise? Clockwise. Yeah. And the weight of the meter stick itself causes maybe a little bit of clockwise. Right? I do have a triple D balance back there. You can measure the weight of your meter stick. Actually, I'll tell you math and brain, but you can figure out the weight from that. Right? What about this mystery weight on the right side? That's definitely clockwise. Right? Because it's way out there. It has a huge lever arm. Right? Do you guys see that the lever arms on each one of these can just be the position is marked on the meter stick? Because it's just everything minus 0. Right? Right. But the spring scale, where you're holding it right here with the spring scale, isn't that pulling back counterclockwise relative to this endpoint? Right. So this is a torque, this is a small torque, this is a torque, and then you're pulling back with a huge torque. Right? You guys see 4 different torques there? Right? And what was the sum of those 4 torques again? 0. So let's go through it. Now here, guys, these 3 boxes can represent 1 torque. These 3 boxes represent the torque caused by the weight of the meter stick. Notice I'm putting the weight of the meter stick at the 50 centimeter location. Right? Here's the torque caused by the spring scale that you're holding up. Right? And notice I call this negative. I'm calling the upward negative and downward positive for the force directions. Okay. Okay. And then, guys, if you add these 3 torques together, suppose you get a number like, -7. I'm just making something up again. Guys, if you get -7 here, guys, look up here. If you get -7 in this box, then what is the last torque have to be? Positive 7. And whatever units, Newton meters, whatever. Right? So that the sum of the torque goes to 0. You guys see that? Okay. And then, same as before, if you know this torque in this lever arm, because it's just in this case, location on the meter stick, take that torque divided by that lever arm. That will tell you the mystery weight force right here. Okay. And if you had hung on a 2 Newton weight, then hopefully this number is pretty dang close to 2 newtons. Okay? You guys get that? Okay, guys good? All right, you guys ready for the back half of this? All right, so here's the poster version of what you're walking through. The simplified version. Okay. And here's the scaffold. Did I tell you guys the story, the Paul Hewitt story related to this last semester? I forget if I did. Because Paul Hewitt, before he went to college and learned physics and was teaching community college, he had a bunch of odd jobs. One of his odd jobs was he was painting signs, like painting billboards, and he was up on this scaffolding. And he was working with another guy who had questions about like philosophy and physics and stuff. One of the things he would do is he would pluck this rope. Guys, look here. He plucked this rope. He said, "Hey, walk back and forth." So as he was walking towards the rope, guess what happened to the tension on this side? Boing, 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 boing. It would go up. He said, walk back to the other side. Boing, 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 boing.
Yeah.
Okay? So now the individual tensions depend on not just how much weight is it holding up, but also where's that weight located. You guys see that? Okay? So that's the overall principle. And here's your framework here. So the sum of the force goes to 0. That just means that the 2 weights down have to match the 2 tensions going up. Right? Now that can't solve the whole thing by itself. Right? But you can with if you bring in torque. Right? But torque, you have to pick a pivot point. Now, this equation exactly, I picked this point right here is the pivot point. Okay. But let's go to your lab and see what this looks like. So now I'm on the side with it looks like scaffolding. You guys see these two? Right. And same as before, I'll go right side first and then left side there. So this one right here says pivot point is the left force, which is right here. Now, it's usually a good choice mathematically to choose one of the force locations as your pivot point because, guys, how much torque does this spring scale cause at that defined point? 0. It's like pressing on the door hinges of a door. It will never turn the door again. Okay? Right, so there are some torques though. By the way, we're looking for the same questions before. I just made a universal question. What's the mystery weight? Now, obviously, you're going to know whatever weight you hang on there. But let's make believe that you don't. And let's use torque to solve for it. You guys get it? So relative to this point, the meter stick says let's go clockwise a little bit. The mystery weight says let's go clockwise a lot. It's probably heavier than the meter stick and also maybe further away. So bigger torque for both of them. And this last spring scale pulls back counterclockwise. So small torque, and then counterclockwise torque. Okay. You guys see 3 torques right there? Okay. Right. So I have some box set up. Now this left spring scale is located 0 centimeters from itself, so it causes 0 torque about itself. I went ahead and zeroed that out for you. Okay. The meter stick weight itself might weigh a little bit, maybe like 1 or 2 newtons. It causes a little bit of torque here. This right spring scale is pulling up, so now you guys put the negative sign. Okay. Guys, let's say you run all this, and it comes out to if you add up these 3 torques, and it comes out to 8 Newton meters, or let's say -8. Guys, if this comes out to -8 Newton meters, then what does the 4th torque have to be? It has to be +8 Newton meters. If this is -8, that's +8, so the sum of the torque goes to 0. You guys get that? Okay. And that would be really something to do with this mystery weight. Now you can get this location by taking this position minus this position, which I told you exactly right here. Okay. And then same as last couple examples, this torque divided by that lever arm gives you that mystery force weight right here in software. Okay. So if you hang on a 2 Newton weight, hopefully this is pretty close to 2 newtons. You guys get that? Okay. Last one. This one right here. Again, you don't have to change the setup. Be identical setup to before. What you are changing is your perspective. Guess here it says pivot point 0 centimeter mark. So now you're doing relative to this point. Now relative to that point, now the left spring scale does cause a small counterclockwise torque. The weight of the meter stick pulls back a little bit clockwise. The mystery weight pulls probably a lot clockwise. And then the spring scale pulls back counterclockwise. These are all torques. Torque, 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 torque. Okay. You guys see 4 different torques now? Okay. You guys, what's the sum of those 4 torques? What does it have to be? 0, as long as it's equilibrium. You just hold it there. Okay. So here's torque 1, 2, 3. You can add up those 3 torques. Now, guys, let's say this number comes out to -5. If this number's -5, what's this number? +5. Okay. And then take that torque, divide by this lever arm, R, and that gives you this mystery weight. Okay. Right, you guys get that? All right, so go ahead. Maybe I'll leave some slides up here. Yeah, you guys got the rest of class and just turn this into the grade tray at the end of class.